Okay, today we're going to take a look at a new technique for calculating limits, especially when the limits are kind of indeterminate of a form where we have 0 over 0 or infinity over infinity. Now, we've done several of these limits in the past, and we had different algebraic techniques for calculating them. But what we want to do is to say, well, what can we do if none of those techniques actually work? So what I want to do is first we'll take a look down at some of these examples. Now I'm going to pause the video and I'd like you to think about techniques that we may have used on these before. There are three limits here that you're going to calculate. In each of these limits, it's an indeterminate form. If I try to check my limit by substitution, which you always try first, when you plug this in, you would get e to the 0, which is 1 minus 1. It's going to give me a 0 on the top and then a 0 on the bottom. So the form of this limit is 0 over 0, which is indeterminate, which remember for everything that we've done in calculus, I'll put this in red, means do more work. That we need to figure out a way to calculate what these limits are. Now, I'd like you to think about this using algebra techniques first. Then I would like you to pick up your calculator, set your table up, and evaluate this expression at 0.1, 0.01, and 0.001, and then use the kind of the estimation technique with the table to guess what you think the limit is. So what do you think it is from algebra? Then pick up your calculator. What do you think it is from the estimation that you see on the calculator? All right, I'm going to pause for about 5 seconds so that you can pause your video and then come back when you're done. All right, so initially taking a look at this, you might go, hey, let's look at what's going, how fast are the top and the bottom moving, kind of compare their relative rates. And when we did survival the fastest, your first gut reaction is to say, well, who wins in the top? In the top, e to the 3x is winning. In the bottom, the x is winning. So we're kind of looking at this term over this term in survival the fastest. And whenever the top won the race, which it clearly is here, we would have made the guess at that point that this is 0, probably. However, unfortunately for us, that is actually incorrect. And so that technique did not work. If you take a look at our actual graph of this, here's the graph of our e to the 3x minus 1 over x. It's coming along. Clearly, the graph as it approaches 0 is not approaching 0. It looks like it's approaching somewhere around 3. And then we can go to the table, set that up, and take a look at your table. Now I have it in ask mode, and we're approaching 0, so we want to try, I think it was 0.1, 0.01, and 0.001. So we can enter those in, and let me delete that one out. And you can see clearly that these values, that it appears to be approaching 3. So if I had to guess, just from the technology that we're doing, I would guess that it's 3. And so really, when you're taking a look at this method, the survival of the fastest method, failed. So survival of the fastest, I've been kind of waving my hands a little bit, saying it's a way to figure things out, but guess what? It's not the best way for a lot of them. It works about 90% of the time. Did not work in this case. What it appears is that e to the 3x is going to 0 about 3 times faster than what x is, which is kind of an interesting fact. All right, we'll come back to this one after we learn a little bit more about L'Hopital and the technique we're going to learn in these notes. All right, now I want to take a look at this one. Again, let's think about what we would have done before we got to this section of notes. We would have plugged in, notice this is a one-sided limit, we're approaching 1 from the right, so that's why I have 1.1, 1.01, 1.01. And then so up here, if I plug in, which is your first thing, your direct substitution, the natural log of 1 is 0, so this ends up being 1 over 0, so our bottom is approaching 0, and this bottom is also approaching 0. And when you have a number divided by 0, it's heading to infinity. So this is actually of the form infinity minus infinity. And remember, that is still an indeterminate form, which again means do more work. So once we recognize that we have this indeterminate form, then we're like, well, what are some things that we might have done? So I'm going to do the same thing I did in the other one. I'm going to pause for about 5 seconds. You guys go figure out some algebra you might do on this. How would you have tried to figure this out without a calculator? And then take a look at it and say, well, how would I figure it out with the calculator and look at the estimate? All right, coming back in, what are some things that we might do? If I have infinity minus infinity and I'm trying to figure out some algebra techniques to work on this, the fact that I have a fraction minus a fraction, one of the do more work things might be do some algebra and try to combine them together. So I possibly could get a common denominator, which would be natural log of x times x minus 1, which would give me x minus 1 minus natural log of x on the top. And then say, hey, did it work? If I combine them together, can I work this out and try to do something else? So we take a look at this limit as x goes to 1 from the right. You're going to end up with a 0 on the top, and you're going to end up with a 0 on the bottom. So doing that left me still with an indeterminate form, which says do more work. So I still haven't achieved my objective of trying to see who's winning. And then you're like, well, it's going to 0. Which one's going to 0 the fastest? And I'd probably say the x is, because log is really slow. So the x is winning here. And then down here, the ln of x times x would probably be the winner. Then the x's cancel. You get 1 over natural log of x, which is going to 1 over 0. And you'll be like, hey, it's going to infinity. So you're trying to reason it out, but even if you thought that was a guess, like, oh no, that's actually going to be incorrect. Let's take a look at the graph. So if I come back over here, the graph of this at 1, you can see right here, this is a scale of over 1 and up 1 here, that it's clearly not going to infinity. There's no asymptote for vertical asymptote there behavior. It clearly looks like there's a hole. So it is going to be a value. And then if you take a look at it on the table, getting closer and closer to 1 from the right side, you see that, oh, well, it does appear to be approaching a number. It looks like it's approaching, if I had to guess, around 0.5. So the technology guess, by looking at it, I would say is 1/2. Clearly nowhere near what we were doing when we were doing our survival of the fastest. Again, another reason why we're going to need a new technique. All right, one more problem down here for you to try before we go to the actual technique. So this one we have as a limit at infinity. So we're kind of looking at end behavior here. If I plug in infinity, which is kind of this idea of checking what's going on, 2 over infinity, this whole term right here is going to be approaching 0. So you're going to have 1 plus 0 or 1. So the inside is going to be approaching 1. And then 1, and that's going to infinity. So 1 to infinity, most of you would probably guess that the answer is 1. And again, that's going to be incorrect. Now, why is this an indeterminate form that's do more work? Is because this value right here is 1 to infinity. 1 to infinity is not actually 1. It's approaching 1. And so, and think about, some things that are going on here. If you're close to 1 but smaller than 1 with a big power, that's a decay. If you are bigger than 1 with a big power, then you are a growth. So you're kind of teetering between decaying and growing, and we kind of made the conclusion that, hey, we're going to 1 because 1 to any power is 1. This is still an indeterminate form. So doing the same thing that we did before, we could take a look at this by looking at the graph and the table, and let's see what happens. So let's come over here. All right, so taking a look at this graphically, when we're going to infinity here, move myself out of the way, that we clearly look like we have a horizontal asymptote. And if I start, just taking a look at the trace, Um, Here at 50, we're about 7.105, so clearly, this it's going to be 1 is not kind of the right gut feeling that you have. If we take a look at our table value here, you can see that at 100, 1,000, 10,000, and so on, as we come down, it does appear to have a limit, horizontal asymptote. It looks to be about 7.389. So the guess from the technology, 7.389, basically is like, oh, okay, then I don't know exactly what that is. That's not a very inexact guess. I am going to tell you that we're going to learn a technique of how to find it exactly. This actually is E squared. And so the idea is the technology and our guesses, our gut feeling is going to send us in the wrong direction. And we do need a little bit of help on this. Now, taking a look at, okay, so now let's go to the next page and let's take a look at some review. And then we'll stop this video and I'll actually start L'Hopital's rule in the next video. But what I would like you to do is to think about what algebra technique. So I would like you to pause the video and I would like you to work these problems. And these are ones that you actually can do with the algebra techniques that we've learned. Try direct substitution, see what form you have. Think about what algebra techniques we had from prior, back when we were doing chapter 2. Work these using the old algebra techniques. And then we'll come back, we'll check your answer, and then we'll start the next video and we'll actually do L'Hopital's rule. All right, so coming back, check your answers with the work that we have here. Your first one, you plug in your -1 and you do get the form 0 over 0. Now remember, make sure that as you are doing this check, do not say the limit equals 0 over 0, because in the AP, that means you're saying that they're equivalent and they're not. 0 over 0 is the form, which means do more work. So you write it over on the side to make sure that they know that the limit doesn't equal 0 over 0, but it is of that form, and which means you're going to choose a technique from that. The technique I chose that we had learned before was factor and divide out. So I factored the top, canceled, removed the discontinuity, took what was left, did a direct substitution, got my answer of -4. Now over here in this one, again, checking my direct sub, I get a form that's infinity over infinity, another indeterminate. I did use survival of the fastest on this one, and when you have a rational function, survival of the fastest is really the easiest thing to do and always 100% works. It's only when it's a little weird, like the ones on the previous page, that it doesn't work. So I took the dominant term of the top, dominant term of the bottom, was able to cancel. The limit as x goes to infinity is 3/2. We also know this because the degree on the top is the same as the degree on the bottom. So in a rational function, you know that the ratio of the lead coefficients is going to be your horizontal asymptote. And then our last one over here, taking a look at it, whenever I plug in 7, I get the form 0 over 0. I use RATCON, rationalizing with the conjugate, in this technique. So I multiplied it out, got the top and the bottom. X plus 2 minus 9 is the same factor as x minus 7. Canceled that out, and then did direct substitution to get my answer. All right, we'll stop this video here. We'll pick up in part 2, where we actually say, now, how can we work these problems using another technique, which is called L'Hopital's rule.